So, this is my introduction to section 6.2. If you look at this, you might see some cubes. And depending on how you look at it, you might see cubes in different ways. For instance, if you're looking at just that, you might see a cube with this end pointing out and that going back. And this is on a piece of paper, so obviously it isn't, but it looks like it. If I look at this one, it looks like this might be the bottom of a cube and this is sticking out. So here we have this sticking out and now we have that sticking out. Now look at both of those. Can you switch back and forth? This pointing out to that pointing out. Now can you make the whole thing switch? This could be pointing out, and this is the bottom. Or this could be in, and this is the top of this cube. All right. We're going into three-dimensional stuff, and so we're going to have to visualize stuff three-dimensionally on a two-dimensional surface. So this could be a challenge. So here I've drawn x plus y equals 1. Goes through 1 and 1, and if I look at the area under this curve, it's this. So if I had that and spun it around very fast, it would make a solid. What would the solid look like? So this, if I spin it around the y-axis, I forgot to say that, y-axis. If I spin it around the y-axis, this would come out, around, and come back in at -1, and then go around behind, and so it would come out, around, and then go behind, and it would make a line over here. And what's that starting to look like? Hopefully you're saying a cone. And what's the volume of a cone? Well, if you put it into a cylinder, the cylinder is the area of the base times the height. Pi r squared times the height. And a cone, the volume is pi r squared times the height times 1/3. If it comes to a point, instead of straight up, it's always 1/3. The pyramid is 1/3 of the box, etc. So, the volume of this particular cone, see the radius of the bottom is 1, so 1 squared is 1, the height is 1, and so the volume of this one is 1/3 pi. But I want to come up with that answer doing calculus. So I'm going to take and slice this. I'm going to think of it as a stack of real thin discs, and each disc is a little bit smaller, stacking up to make the top. So I'm going to, it's kind of like I'm taking a cheese slicer, and this is a hunk of cheese, and I'm slicing off slices. And each slice will be a shape of a circle. Now the slice, although thin, will still have some height. And the height, since it's in the y and it's a really thin, I'm going to call it dy as the height. A small change in y, dy. And it'll have a radius. It's in the x direction, and if I were finding coordinates on this line, they would be x, y. So the radius is x of this disk. The height is dy. It's basically a cylinder. So the volume of this disk is pi x squared dy. And I want to add up all the disks that are stacking up to make this from y starting at 0 and going to 1. And if I do this correctly, I should get 1/3 pi. This is y. These are the limits for y, but there's an x in here. So I have to replace the x with an equivalent expression that has y in it. If I look at the original equation for this line, x plus y equals 1, well, x would equal to 1 minus y, so I would have the integral from 0 to 1 of pi is a constant that's times it, so I can pull it out. X squared would be 1 minus y squared dy. Now I could do a u sub for the 1 minus y, but I can also just multiply this out, so I'll have pi integral from 0 to 1 of 1 minus y times 1 minus y. I have to do the distributive property. I'm going to get four things. I'm going to get 1 minus a y and minus y, so that's minus 2y plus y squared. So now if I integrate this, take the antiderivative of this and evaluate it from 0 to 1, I'm going to have pi times antiderivative of 1 would be 1y, since I'm doing with y. Antiderivative of negative 2y would be negative y squared. Antiderivative of plus y squared is plus 1/3 y to the third. Evaluated from 0 to 1. And that is the values for y, and that is y inside. If I put in 0, I'm going to get nothing. So I'm going to get everything from when I put the 1 in first, which is going to be pi times 1 minus 1 plus 1/3. And the 1's cancel, and I get 1/3 pi, which is what I thought I should get. Okay? So I'm able to find the volume of a solid that's a rotation, a solid from a rotation, by slicing the solid into disks and using the idea of the volume of a disk is like a volume of a cylinder, pi r squared times the height. Okay? So now I'm going to go to a circle, which I hope you remember is x squared plus y squared equals r squared. R is the radius of the sphere, the circle. Any direction I go is capital R. So, out to here is capital R, 0. Up to here is 0, capital R, etc. So I'm going to just look at the first quadrant here, this, and I'm going to spin it around the x-axis. I could spin it around the y, but I want to do it around the x-axis this time. So this area spun this way is going to come up, around, and go down, and then go around behind and back, and it's going to create a hemisphere, half a sphere. Now I'm going to take a slice of this because I'm rotating it around the x-axis. I'm going to slice it perpendicular to the axis. So I'm going to make use my cheese slicer perpendicular to the axis of rotation, like I did here. The axis of rotation was the y-axis, so I sliced it perpendicular to that. Now it's the axis of rotation is the x-axis, so I'm going to slice it perpendicular to y. And what I'm hoping I find is the volume of a hemisphere, which would be half the volume of a sphere, the whole sphere. All right, so a slice hopefully you can see, would be a circle coming out and then going back. It's actually a solid circle. It's filled in middle, so it's more like a disc, a coin, if you will, that has a thickness that's very thin, infinitely thin, but the thickness is now in the x direction, so the thickness is dx. The radius is from here to there. Now that's not the radius of the sphere, which is from here to any place on here. I'm talking about the radius of the disk. So that's a different r. So the volume of this disk is like the volume of a cylinder. Pi r squared h is the volume of a cylinder. So I'm going to have the pi. My radius is in this direction. It's going to a point on the circle. The point has got an x-coordinate and the y-coordinate. This is the y, this is the x. So it's going to be y squared times the thickness, which is the height of the cylinder, is just dx, a real thin height. It's really short, like a coin. This would be the thickness of the coin. This is the radius of the coin squared times pi. And I want to add all of these up. Now I'm going in dx, and so my dx is going to go from 0 to capital R. But it's x, and I've got y in here. So now I have to replace the y squared with what it's equal to. And it has to have x's in it. Well, if I subtract x squared, that's what y squared is. So I could solve for y, which would be the square root of r squared minus x squared, and then I have to square it, or I can just say y squared is r squared minus x squared. So this integral becomes the integral or antiderivative of 0 to r, definite integral. Pull the pi out, y squared is equal to r squared minus x squared dx. Now, some people mess up here. They say, oh, I'm going to integrate the r squared, and they're going to say it's 1/3 r cubed. R is not the variable. R is the radius. This r is the radius of the big circle, and that's going to be a constant. And so when we integrate a constant, it becomes the constant times x, the variable. And then we integrate the minus x squared, which becomes minus 1/3 x to the third, evaluated from 0 to r. So I plug in r, and we get pi. R squared times r is r cubed, minus 1/3 r cubed. And then we plug in 0, and we get 0, so I don't have anything to subtract. And so I have 1 r cubed minus 1/3 of r cubed, which is 2/3 of an r cubed times pi. So the volume of a hemisphere is 2/3 pi r cubed. And if I double it, I would get the volume of a sphere, and you should know the volume of a sphere is 4/3 pi r cubed. So because of the symmetry, I was able to find the volume of a sphere using just the hemisphere, and did a slice perpendicular to the axis of rotation. Now I could have done the slice this way, and it would be all analogous, except I'd be going for the thickness is dy, so I'd have to express it with y. The symmetry here would make it be the same kind of integral. It would be r squared minus y squared. Okay? So now, what if we had y equals x squared, which I believe you know is a parabola that goes through 0, 0, goes through 1, 1, goes through minus 1, 1, parabola. Slope here should be 0, so it shouldn't be any pointy to it. And 1/2 x cubed. So that goes through 0, 0. Goes through 1/2. If you put 0 in for the x, we get a half. If you put 2 into it, 2 cubed is 8, divided by 2 is 4. So it goes through 2, 4. So it goes something like that. And it goes down here. I'm not going to be concerned about that. I'm going to look at this piece in the first quadrant. And I'm going to try to imagine what that looks like if I spin it around the y-axis. If I spin it around the y-axis, this point would go over to there and then back around behind and come out. This point would come over to here and back around, and this point would come over to here and back around. Okay? So I hope you can see that this would be some sort of bowl with a very thin bottom and a very sharp edge at the top. So let's say this bowl is made of glass. How much glass does it take to make a bowl? That's the area between these two curves spun around the y-axis. So this, what I just drew here, and that causes this to be a thin shape here. But it makes a disc with a hole in it. Well, a disc is going to have a thickness, it's in the y direction, of dy, and it's going to be a cylinder minus the inside cylinder. Okay? So the volume of that disc is going to be pi r squared minus pi r squared times the height, and both of them would be times the height, which is dy, where r is the large radius, capital R, and my small r is the radius of the inside. Now, the radius of the large one is just in the x direction. It's the x on that curve. So what is x on that curve? So if I solve for x, multiply by 2, and take the cube root, that would be the large r. And the small r would be just x for the other graph, because it's over x up y, over x up y to the curves. And so I have to solve for x, and I would get the square root of y is x, which is the small r. So the volume of the full disk would be the integral, or would be pi big R, which is cube root of 2y squared, pi r squared, times the height. And the volume of the inside disk would be pi small radius squared dy. And if I add up all the disks and take away all the centers, I would get the volume of the bowl made out of the with the sides, the thickness of the difference between the curves. So, working this out, yeah, I think I will work this one out. what would my limits be? Well, I'm doing y, and y has got to go from 0 up to 4 for both of them. So I can write this all together as one integral, and I can pull out the pi's of both of them, so I'd have pi integral from 0 to 4 of, let's see, this is cube root, which is 1/3 power squared, so it's 2 to the 2/3 times y to the 2/3 dy minus, and this would be, I pulled the pi out, so I'm putting these together, the square root of y squared is just y dy. This would be for the inside, pi this, and for the outside washer is that, outside of the washer. And so the volume of the washer with the hole missing is what this is, which is pi, the 2/3, 2 to the 3/2, the 2/3, excuse me. And the antiderivative of this is going to be, have to add 1, which is 5/3, so it's 2/5 y to the 5/3 minus 1/2 y squared, evaluated from 0 to 4. If I put in 0, I'm going to get nothing, so the volume of this is going to be pi. If I put 4 in here and square it, I get 16. I get the cube root of 16 times 2/5 times 4 to the 5th, and then take the cube root. So 4 to the 5/3 minus 4 squared is 16, cut in half, minus 8. And if I put in 0, I get 0. So that's the volume of the glass of this bowl. Now, what if I spun this area between these two curves not around the y-axis, but around the x-axis? So this would go from 2, 4 down to 2, -4, and there would be the two curves out like this, and it would be, so it's just kind of a bullhorn, or if you set it down, it would be come up to a point. I don't know what you want to call it, but I hope you can imagine what it is. Maybe it looks like the top of a martini glass, if you have no idea have an idea what that is, if the stem went this way. But anyway, it goes this way. So if I'm going to do a slice on it this way, I would do it perpendicular to the axis, which would be something like this. And I'd have the outside, the big radius, and the inside. The thickness of the washer on this would be d, the thickness is in the x direction, so dx. The large radius goes up to this curve, and it's y, so it would be the integral of pi r squared, which is y squared, for the large radius, times the thickness, times dx, minus pi times the small radius, which is the y from this one, y from the inside, squared. So this is the outside radius, and the inside, dx. But it's x, so I have to get these in terms of x. And my limits are, well, I'm going to go from 0 to 2. If I'm just doing this. So, To clean this up, it's going to be pi integral from 0 to 2 of the y for the outside goes up to the x squared, so y squared would be x to the 4th minus, for the inside it's this, and if I square that I get 1/4 x to the 6th, because it's got to be y squared. So that squared is 1/4 x to the 6th. Now, will the volume of this object spun around this way be the same as this? And I think not, because this is spread out wider than this one is, so it takes more glass to make the bigger circle than for the smaller circle. So I'm thinking they're not going to be the same. It might be coincidentally the same, but I don't think it will be. This will be a little bit easier integral to do. It's going to be pi x to the 4th becomes 1/5 x to the 5th if we take the antiderivative, and this becomes minus 1/28 x to the 7th, evaluated from 0 to 2, which would become, putting 2 in here, we get 32/5 minus 128 over 28 minus 0. And these two are not going to be the same. But there's an exact answer for the volume of the one where that spun around there. And that's about as far as I got today.